Good afternoon. I need a little more juice on here, please. Okay, thank you. Was that allowed? Good afternoon? Oh. Let's do it again. Good afternoon. Okay, great. Thank you, thank you, thank you. So we have talked, or you have talked the last time I wasn't here, you have talked the last time about polymerization where you had hexamethylene diamine and cypazoyl chloride, and you put them together, and then they made these long chains molecules, and it wasn't very well visible on the B-space, on the webcast, but so they hooked up together here, and they made a long chain, and I think John was even standing on the table trying to pull it out. One could see it. And so what you need to know is, what is the steric number and the electron configuration on, for example, this nitrogen? What is the steric number on that nitrogen? 4, okay? And what kind of a structure would that be? 4, okay? What kind of a geometric structure would that be? Tetrahedral, okay? That was close, though. Okay? And now if you look at this carbon here, what would that be in the electronic structure? Steric number? Steric number, VSPR, remember? Loud. 3, okay? Steric number 3. And geometry? Trigonal planar, the angle in between? You got to practice this, or you got to wake up, one or the other, okay? So you then talked about isomers. There are different kinds of isomers. There are structural isomers. They have the same number of atoms, the same molecular mass, but they are total different compounds. So you have this here, for example, it's a very delicious compound for sometimes heavily used in our society. And so this it looks like this, and this is dimethyl ether. This is not so delicious. When you take this, you will fall asleep. That's what they used for anesthesia in the 50s and 50s. Still, I got a surgery where this was used. So you were not sick from the surgery, but you were sick from this. They poisoned you essentially. It took you about 9-10 days to get really back, and so we're not doing this anymore. That's good, but it might explain a lot of things in older people. Anyhow, then these are very different isomers. These are structural isomers. They have nothing in common except the number and type of atoms that are combined in the molecule. And then you have some very subtle differences. These would be stereoisomers. You have 2 carbons here and 2 chlorines, and then 2 hydrogens. So this would be a trans configuration. Trans comes from across, okay? This is Latin. It comes so they are across from each other. The hydrogens are across from each other. And the isomer for this here would be a cis configuration, and cis means on this side. So they're on the same side. And so these are stereoisomers. They have some kind of differences. One of them would have a dipole moment, for example, and the other one wouldn't. Which one would be the one with the dipole moment? This one here, okay? That's the cis isomer. This one cancels the moments here between the molecules. And this would be a structural isomer. It still has the same number of carbon, same number of chlorines, same number of hydrogen, but here the chlorines sits on the carbon and the hydrogen on the other carbon. So this is the case of structural isomers. And you then have talked about isomers, very specific isomers, about chiral isomers. And chiral molecules have isomeric structures that cannot be superimposed. They are mirror images of each other. Chiro comes from, chiro is the Greek word, means hand, okay? And so we say that they have a handedness. So we have a handedness. We are chiral. So we have a left and a right leg. We have left and right hand. And only superimposing, if I have a mirror image here, this would be, I can superimpose that. But this doesn't work here, all right? This does work, but this doesn't work, okay? So if I have it in this orientation. And so we are very chiral. And chirality is actually a fundamental property of biological molecules. It's very, very important. And the body, so if it's chiral, there must be the possibility of 2 forms. And let's go and look at this here. One form, for example, if I could get big up on the screen here, please. So a chiral molecule has one center atom, and it has 4 different things. 1, 2, 3, 4. Oh, they're not different. So they're not chiral, okay? I can superimpose them, green to green, brown to brown, and white to white. This has center and 1, 2, 3 different things. This and this is the same. So that's not chiral, all right? A chiral molecule would be something like this. It has a center, it has 1, 2, 3, 4 different things. That doesn't have to be necessarily only one atom. There could be a whole chain of atoms there. So there's no way that I can make this the same with another molecule. So this is a mirror image of this here. And if you look at the mirror image here, so you see you go here, and you pull the mirror image out. There it is, okay? Not very impressed, you guys. And so let's see that I don't screw this up totally. That I get this, I can brown, and you've seen it before, of course. Brown and magenta fits, but now the green and the white doesn't fit, so I can't get it together. I can make the white and the green fit if I can. And let's see, the white and the green, and white and the green. Now these 2 guys are not fitting, okay? These are chiral. And they have usually, or very often, chemical organic reactions. They make both forms. So they call it enantiomers. This is an enantiomer to this. And if you have them both together, that's a racemate, a racemic mixture, okay? And maybe I should walk you through a little bit here, and before I tell you about the racemates. So these are enantiomers. This is the enantiomer to this here. The only one that is, so one would be left rotating and one would be D-type, and left and D means L is levo, that means for left actually, in I think it's Latin, and dextro is D, that means rotating right. What does it mean? It's not going to rotate like this, but if you shine light on it, then it rotates the light to the left. This would be to the right for you to the left, for me to the right. Okay, it turns the light to the right or to the left, L and D. And this was discovered by Louis Pasteur, a very famous French chemist, and also he did a lot of biology. And he discovered this phenomenon of chirality. And this phenomenon, he lived from 1823 to 1895. And so if you have this handedness I explained to you, there are non-superimposable only mirror images. You see, that would be that's not superimposable, what I just shown to you. So let me tell you about this enantiomers or racemates. If you have a pharmaceutical, for example, statistically, it can make both one form, the D and one the L form. Usually it's 50-50. Sometimes it's a different distribution. But the body only recognizes one form, okay? L-glucose, for example, is not recognized by the body. You need a D-glucose, actually, to do something with it. And so this is the case also with pharmaceuticals. And so they have this mixture in there, and they market this, and it has both of them in there, but the body only recognizes one, and the other one you excrete right away without that anything happens. And so when the patent runs out, they say, okay, now we separate those. We take the one which is not so good, which doesn't do anything, we take this away, and now we sell them only the one enantiomer, and we give it a different name, a slightly different name, and we patent it again, and then we have to patent for some longer time, and the generic pharmaceutical industry cannot get their hand on it. The other thing would be, of course, amino acids. The body recognizes only L amino acids, okay? So you build proteins from the L amino acids, so you could feed a guy D amino acids. actually, he would probably feel satisfied from eating, but he would starve that person to death because he would eat a lot, but he would not get any nutrition from it because there are no proteins being built and so on and other things that are in the body. So if you, for example, look at I think it's sucrose. I'm not sure if it's D-sucrose. I think it's D-sucrose, which the sugar, recognizes. And so the moment it has several OH groups, and there people substitute these OH groups with Cl, actually 3 OH groups, they take 3 Cl groups instead, put on there, and suddenly the body doesn't recognize it anymore. And this is called sucralose, and it's called Splenda, okay? It tastes sweet, and it's satisfying, but it's not going to get into your system if the body doesn't recognize it, it flushes right through, okay? So far, we are all chiral, and chirality is a very important thing, and what I want to say to you, you need to be able to recognize chirality, all right? So you need to practice this a little bit. So today, we're going to talk a little bit more about bonding. Oh, not again. And so bonding is, we have looked at this at the moment as the valence electrons, how they bond with each other. And so if we position them right and then they overlap, then they bond. And this is very simple. You can do this for the first and second and sometimes for the third group. Then the Lewis method has some exception octet expansions or doesn't reach the octet, the central atom or some of the atoms. And so this works pretty well. But there is something which is called molecular orbital theory, and this explains a lot of other things. And so you remember, what does this really signify? This obviously is an s orbital. And the s orbital, remember, this is nothing but a wave, a standing wave. And this shows us the probability to find that electron as part of the wave, okay? And so we have, remember, we had this Schrödinger equation that we solved. We didn't solve this, but this is sort of pictorial solve. We solved the Schrödinger equation. It gives us n and L and m sub L and m sub s. And with this, you have the energy state and that waveform, okay? And the waveform gives you what kind of orbital it is, the shape and other things. And so when you have that wave here, so waves, they can interfere with each other. They can constructively interfere when they are in phase, and when they are out of phase, destructively interfere. Remember, when they constructively interfere, what happened? What happened to the amplitude? It was added up, the amplitude. And so now we have this larger wave function now. Before we had these smaller ones, the two interfere constructively. We have a larger wave function, or wave, not even a wave function, we have a wave. And so now you square, you have only positive lobes. And when you plot this, now we have a higher probability to finding this electron. Are you with me? Okay, good. And so if you look at this, for example, here, we have here a 1s orbital. And usually, and if you looked it up in the web, I gave you a demonstration, the 1s orbital went red and green, and red, or blue, and red and green, and red and green. That shows you that's a wave. There's a positive, negative lobe, and so on and so on. But since it's spherical, you can see it very well, okay? So this is why it has this red there. The red can come out, and the green goes away. That's the wave, standing wave. So that hydrogen would have one electron here. Is that right? That would be a hydrogen atom, most simple one electron system. Now, if you have a second hydrogen, and they are now in phase, so they can constructively interfere. So that's why it has also one electron. So now let them constructively interfere. So we have a linear combination of the atomic orbitals to make a molecular orbital. We combine them through the interference and make a molecular orbital, and this looks like this. So now, I already gave you a clue. This molecular orbital, so they have bonded, the two hydrogens have bonded together. This is how this molecular orbital looks like. Would it be higher in energy or lower in energy than the individual hydrogens? Lower, because bonding, you will release energy. And this gives us a molecular orbital, okay? So you put, this is a molecular orbital here, and we call this type of bonding with S's, sigma, we call this sigma bonding, because that's a Greek S, sigma is a Greek S, so that forms a sigma bond. If you have these bonding together, that's how it looks, but we can't lose orbitals. So we have two orbitals here, and we make one sigma bonding molecular orbital. So that's just down here, all right? Now, what happens if this is different phase than this one? So this would be red and this would be green. What would you get there? Destructive interference. And this we call anti-bonding molecular orbital. So this would be higher or lower in energy than the initial ones? Higher, okay? So why would that be? This is the anti-bonding sigma star molecular orbital, and it goes here, and we put a sigma star in there. That's the sigma bonds, sigma star anti-bonding. And you can say, this has a, what is it, does it have? A node, exactly, actually, planar node, actually. And so this got to be higher in energy. Remember that? And with this, we have the simple s orbital molecular bonding explained. So let's practice this a little bit. So you have hydrogen, and paramagnetic means that it's magnetic. And diamagnetic means that they are in opposite the electrons, and they are not magnetic, okay? So this is magnetic. And now you follow your Hund's rule, and you also follow your DeWitt rule, and you follow your Pauli principle, okay? And you do the same thing. You fill the lowest ones first, and then you fill the higher ones. So you go, I put this one here, and I put this one here, so they have to be opposite spin, otherwise I violate my rules here, my Hund's rule. And with this, I get H2, and I get the bonding sigma molecule. There's nothing in the anti-bonding molecule orbital. Nothing, okay? So it didn't form, actually. So now we can say we have a bond order. Remember, we had bond order 1, 2, and 3, and something in between when we had these resonance structures was 1, 1/3, and 1, 1/2. So a 1 means one single bond. Bond order 2 means double bond, and bond order 3 means triple bond. So the double bond is not twice as strong as the single bond, but it is much stronger than the single bond. And the triple bond is not 3 times as strong than the single bond, but it's stronger than the double bond, quite substantially stronger, and of course it's much stronger than the single bond, okay? So if the bond order is 1, 2, or 3, then you see, this must be single, double, or other bond. If it's fractional, then there must be something else. So the bond order in this molecular orbital theory is the number of bonding electrons minus the number of anti-bonding electrons divided by 2. There is 1, 2, these are bonding electrons, this is 2, minus the anti-bonding electrons is 0, divided by 2, bond order is 1, okay? Single bond. All right, let's do this. And this one is paramagnetic, and this is diamagnetic. So this is not magnetic at all. Let me explain to you this about the magnetism. I said if you're paramagnetic, you have unpaired electrons. If you're diamagnetic, you have paired electrons, and you're not, that's not you. But the molecule or atom is not magnetic, okay? And so this is a magnetic susceptibility measuring device. This is just a principle. It's a very sophisticated device. Essentially, you have a balance, and you have hooked to the balance your sample, and you have glass tubing, and you can evacuate it. And then you have an electromagnet. And if this is paramagnetic, you switch on this electromagnet. This will be pulled into the electromagnet, and you get your reading, and the reading will be giving you the magnetic momentum, okay? If you have a diamagnetic molecule where you have paired electrons, you can switch on that magnet as much as you like. Nothing will happen, okay? Because it's not magnetic. So this is magnetic susceptibility. Coming back to our bond order, we have done this here. Now, let's do this with a couple of other molecules. So this was helium. Let's do helium. Helium has one s2 configuration, one s2 here. So we want to bind two helium together with molecular orbital. So we put bonding and anti-bonding orbital, sigma and sigma star. So we have one in here and one in here. So now we have two left. So we have the other two in the anti-bonding molecular orbital. So that would look like this. What would be the bond order of this? 2 minus 2 is the antibonding, is 0, divided by 0 is still 0. So helium-2 bond order 0 shows you it doesn't exist. Okay, it can't bond because helium is at the end of your on the period here, so there's no helium-2 molecules. Okay, that's what it shows to you. Now let's play a little bit more. Let's do lithium. Lithium is in the 2s. The 1s2 is filled, and now we look at the 2s1. Lithium has 2s1, each is 2s1. And we put in the bonding molecule order, we only have one on each side, so that's bonding up and down spin, and the antibonding is empty. What is the bond order there? 2 minus 0 divided by 2 is 1. Lithium exists. Lithium is a single bond. And beryllium. Beryllium is 2s2. Did I say 2s2 for this one here? No, it was 2s1, okay? Did I say 2s2? No. Okay, 2s1. Yeah? So this is 2s2, beryllium. So we have 2 on the left side, 2 on the right side. Are you with me? Of course, they're not like this. They're like this and like this on each side, okay? And so now we form the molecular orbital. We have the bonding sigma and the antibonding molecular orbital sigma star. So we have 4 to distribute. We put 2 in the lower one first, at the spin, and 2 in the upper one, in the antibonding. So what's the bond order of this? 2 minus 2 is 0. Doesn't exist, okay? So you'll get the drift. Bond order and bonding and antibonding. This is just s orbitals. And let's play with s orbitals a little bit. With s orbitals, I have hydrogen, helium, we did just this, and lithium. I just did that, didn't I? Okay, now I ionize this. So I have to take one electron away here, one electron away here, and one electron away here. So which becomes more stable when you have it ionized? So you compare the bond order before ionization to the bond order after ionization, and then you see if you had an increase in bond order, then it must have been more stable. Why don't you give this a stab, please? You're done, okay? Stop sleeping, Professor, okay? Okay, there needs to be really some explanations there. This is a Gaussian distribution. Now, you should be able, there's hydrogen. What's the bond order on this here? 2 minus 0 divided by 2 is 1, okay? What's the bond order on this one? Helium. 2 minus 2 is 0 divided by 2 is still 0, okay? What's the bond order on this one? 1, okay? So this is 1, 0, 1. So now take one electron away here. Take one electron away here. Got to take it away, right? Okay. And take one electron away here. Be ionizing, isn't it right? Ionizing, which upon ionization, that means there's an electron missing. And then determine the new bond order and compare it to the old bond order and see which one increased. Okay. Why don't you discuss this with each other? So what's the answer? What's the answer? Again, yes, okay. All right, so bond order, it's a very simple concept. And so let's see what we have here. That bond order was 2 minus 0 divided by 2 is 1. That bond order was 2 minus 2 is 0. Its bond order is 0, okay? Doesn't exist, okay? That bond order, but if it doesn't exist, you still can compare it, okay? That bond order is what? 1, thank you, okay? And let's see if you're right. Yes, we are right. Oh, wonderful. Okay, now we take 1 away here. What's the new bond order here? So 1 minus 0 divided by 2 is 0.5. Now we take 1 away here. 2 minus 1 is 1 divided by 2 is 0.5, is that right? And this one is 1 minus 0 divided by 2 is 0.5. So they're all 0.5, is that right? I even take the electrons away. There you go. Okay. So which one became more stable? B. Actually, this is true. There are molecular beams.